Hi all, so welcome back to the lecture series on solving previous year questions of GATE ECE, and this is the fourth part where we are solving the questions related to analog circuits, especially the circuits related to MOSFETs and BJTs. Okay, so let us start today's solving. So this is the first question and this is from GATE 2021. So the question is, in the circuit shown in the figure, the transistors M1 and M2 are operating in saturation. The channel length modulation coefficients of both the transistors are non-zero. The transconductance of MOSFET M1 and M2 are GM1 and GM2 respectively. And the internal resistance of the MOSFETs M1 and M2 are R01 and R02 respectively. Ignoring the body effect, the AC small signal voltage gain dV out by dV in of the circuit is. So the question is like we have been given this MOSFET, that also PMOS based circuit, okay, and we have two transistors M1 and M2, and M1 is having a transconductance of GM1 and M2 is having a transconductance of GM2, and both the transistors is having an internal resistance, that is output resistance R01 and R02, right? And the question is to find V out by dV out by D in. Okay, so what we will do, we will draw the small signal equivalent of the circuit. Okay, so sorry, so first we will draw the we'll replace M1 and M2 with its pi equivalent, right? So we'll first draw here the pi equivalent of M2. So okay, so this is for M2. So I will just, so this is gate terminal of M2, this is drain terminal of M2, and this is the source terminal of M2. So this is the VGS of M2, so I will call it as VGS2, and so this will be GM2 into VGS2, and this resistance is R0. Okay, and here I will draw the pi model of the M1. Okay, so this is R02, so this is R01. So I have gate, drain, source, okay, and this is VGS1 of transistor M1, and this is GM1 VGS1. Okay, so we'll just connect it. So first we'll see, so this is corresponding to M2 and this is corresponding to M1. Okay, so the gate of the M2 is connected to V in, right? So here I have connected V in to ground, yeah. Okay, and what happens to source? So this is the source, right? Source is connected to VDD. So in small signal we have to short circuit this DC voltage, right, VDD to ground. So the source will be connected to ground. Okay, and the drain is connected to V out. So where is the drain? Drain is V out. Okay, now we'll connect M1. So here the gate of M1 is connected to ground, so this gate is connected to ground, and drain is also connected to ground. So this is the drain is connected to ground, and the source is connected to the drain of the first M2, right, transistor M2. So I'll connect like this. Fine, so I can just redraw this, right? So if you see here, so this is the V0. Okay, so this to ground is V0. So this terminal is now V0. Okay, this terminal is V0. So what is here? VGS1 here. VGS1 is actually equal to minus V0. Correct? And so I can redraw this once more. Okay, so I will first draw the M1 transistors model as such. So here if you see, the source terminal is grounded and the VGS is same as Vin, right? So I can, instead of VGS2, this is same as Vin, right? So this is gate, okay, and source. So instead of, okay, yeah, let it be, we'll come to that. Now I can draw the second part. So here the drain is connected to the source, right? So I will draw this source end as like this. This is the source. So this is the drain of M2. This is the source of M1. Okay, and from there I have the signal, not signal, I mean the current source GM1, VGS1. So it is like this, correct? GM1, VGS1, because this current is flowing towards the source right here as per the circuit. And this, okay, I'll just replace VGS1 as minus V0, so it will be like V0, so minus of minus V0, okay. And the next terminal is actually connected to ground, so I can connect this to ground, okay. And here I have R0 also, from source to drain or the ground I have R0 1. And what is V0? This is V0, okay, or I can say this is actually now V0, right? Yeah. Now if we see here, okay, if we see this is like across this I have the voltage V0 and this current is like minus GM1 V0, which means the current is flowing in this direction. And since it is across the dependent source, it's the voltage is V0, I can replace this using a resistor, right? And what is the resistance value? It is 1 by GM1. So current is like V0 by 1 GM1, that is GM1 into V0, right? So I'll just redraw this circuit once more, okay. So I can redraw like this, GM1, VGS2, or here instead of VGS2 I can write as V in itself, right? VGS2 is same as V in, so V in, right? So this is now V in, okay. And here I have R0 2, okay. Now this point I will change this dependent source to 1 by GM1, right? And I have R0 1. So the voltage across this is V0. So from the circuit it is very clear that these resistance are in parallel. So it is like net resistance is R0 2 parallel 1 by GM1 parallel R0 1, okay. And this current is flowing through this parallel resistance, right? So what is V0 here then? So according to this circuit, V0 will be equal to, since current is flowing like this, right? So voltage drop will be plus minus like this. So V0 will be equal to minus GM1 V in into this resistance. So R0 1 parallel, R0 2 parallel 1 by GM1, or V0 by V in will be equal to minus GM, I have done mistake, this is GM2, sorry. So this is GM2, okay. So that into R0 1 parallel R0 2 parallel 1 by GM1, right? So this is the V0 1 by V in. So the option is D, okay, minus GM2 into 1 by GM1 parallel R0 1 parallel R0 2, yeah. So this is how we solve that question, okay. So let us go to the next question, again that is from GATE 2021, okay. So the question is, for the transistor M1, oh sorry, okay, sorry. So the question is, for the transistor M1 in the circuit shown in figure, mu n COX equal to 100 microampere per volt square and W by L equal to 10, where mu n is the mobility of the electron, COX the oxide capacitance per unit area, W is the width and L is the length, okay. So here for M1, mu n COX is 100 microampere per volt square, okay, and W by L is 10, okay. The question is, the channel length modulation coefficient is ignored if the gate to source voltage VGS is 1 volt. So given this is 1 volt, okay, to keep the transistor at the edge of the saturation, then the threshold voltage of the transistor rounded off to 1 decimal place is. So given VGS is 1 volt, okay, so then what should be the threshold voltage, so that it is working at the edge of the saturation. So we know, so this is the DC cara, so ID versus VDS. So it will be something like this, right, as VDS increases. So, and it is working at some VGS equal to 1 volt. It is mentioned that it is working at this edge. So what is at this edge means the edge is at which VDS is equal to VGS minus VT. This is the edge, right, where VT is the threshold voltage. Okay, so we have to find this VT. Okay, so from this circuit we know there will be a current ID flowing like this. Okay, and what is VDS here? VDS is the voltage across this, that is VDS is equal to V out itself. Okay, so from the circuit VDS is equal to, right, the above voltage is 3 and there is a current flowing from top to bottom, so there is a voltage drop like this, okay, and that voltage drop is ID into RD. So I can say like 3 minus this ID RD will be the remaining voltage at this point, that is equal to VDS. Okay, so I can write like VDD minus ID RD, that is the sorry, IDRD. Okay, now given in the question VDS is known, okay, so VDS is, sorry, okay, from the question VDS is equal to VGS minus VT because it is working at the edge, okay, and VDD is 3 minus, what is ID? ID is since it is at the verge, I can write like 1 by 2 mu n COX W by L into VGS minus VT square. Okay, so this is ID, that into RD is 20k. So if I substitute here, so VGS is given, VGS is 1 volt minus VT equal to 3 minus, okay, this 2 cancelled, so it will be 10k. Mu n COX is 100 micro, so 100 micro into W by L is 10, that into VGS is 1 minus VT, okay, that is into 10k. Okay, so I can write as 1 minus VT, okay, equal to 3 minus, so 100 micro into 10, that is 1000 micro into 10k, so this will be approximately equal to 10, right. So this will be equal to 10 into if I expand this, it will be 1 minus 2 VT plus VT square, right. Now if I expand this, this will be equal to 3 minus 10 minus 20, not minus, plus, right, 20 VT minus 10 VT square. Okay, if I bring the RHS to LHS and rearrange, I will get it as 10 VT square minus 21 VT plus 8 equal to 0. Okay, so it's again a second order equation. So if I solve this, I'll get VT as, so it will be like minus B, right, so plus 21 plus or minus root of B squared is 21 square minus 4 into AC, 4 into 10 into 8 by 2A, so 20. So if I solve this, I will get two values, either 0.5 volt or 1.6 volt. Okay, so which must be the correct value. So if it is 1.6 volt, this is greater than VGS, right? So definitely this won't be the value. Here it is less than VGS, then only it will work. So this is the correct value. So right answer is 0.5. Okay, so correct answer is 0.5 volt. Okay, so this is how we find the VT, threshold voltage, of this question. Okay, okay, now next we'll go to the next question, third question. So this is from GATE 2020. So okay, we'll see what is the question. Given for the BJT in the amplifier shown below, VB is equal to 0.7 volt. So here this is a base, right? So VB is 0.7 volt. Okay, KT by Q is 26 millivolt. Assume that the BJT output resistance R0 is very high and the base current is negligible. Okay, so IB is approximately equal to 0. So which means IB approximately equal to 0 means IC is almost equal to I, or IC is equal to I, right? Yeah. The capacitors are also assumed to be short circuited at signal frequency. The input Vi is direct coupled the low frequency voltage gain V0 by Vi of the amplifier is. So question is to find its small signal gain. Fine. So to know the small signal gain, what we will do, we will just convert this circuit, right, to its small signal model. So I will just convert, I will just draw the BJT with its pi model. Okay, pi model equivalent. So this is the pi model equivalent, and given R0 is very high, so let it be like this. So this is the base terminal, this is the collector, and this is the emitter terminal. So this is R pi, and voltage across this is V pi, and this is GM V pi. Okay, okay, so we'll start with the gate, base. So base is connected to V in, so I will connect a V in voltage here. Okay, emitter is connected to a resistance to minus 10 volt. So I can short circuit the minus 10 volt to ground, and since the capacitors short circuits at the signal frequency, this is short circuited, right? So actually RE will be 0 now, like not RE, the equivalent across this node will be now 0. So I can connect this emitter to the ground itself. Okay, because the capacitance is short circuited to ground, right? And in the small signal equivalent, this is connected to ground. So effectively the voltage across this node will be ground. Okay, now what happens to the collector node? So I have a resistance RC to 10 volt. So again this is also set to ground, right? So there is one resistance RC, that is 10K, connected to ground, and this capacitor is also short circuited. So I have one more resistance, that is 10K. Okay, so I have all the values except GM. Okay, the value GM is not here. So what I have to do is, like, I need to find the GM from this circuit. Okay, so if I draw, I will redraw this circuit. So how to find the GM? So GM, we know GM is equal to the collector current IC by the thermal voltage VT, that is KT by Q. Okay, so I just need to find IC value. So for that I have to represent the circuit in its DC model. Okay, so that is, we will disconnect all the, or we will replace the small signal or the signal with frequency with its equivalent circuit resistance. That is, we will short circuit the voltage sources and open circuit the current source, that also signal with frequency. Okay, so here I will connect only the DC value. So here I have 10 volt, Okay, so here I have minus 10 volt, and this is connected to, sorry, ground, and this is 0.7 volt. Okay, so if I know this current IE, that is same as IC. Okay, so here it is 10k, right? So from this, what is IE? IE is the current through this resistance. So I just need to find what is the voltage across this resistance, RE. So from the circuit, it is clear that here it is minus 10 volt. Okay. So what is the voltage across this resistance? The voltage at this node minus this node. So if you see here, the voltage at this node is minus 7, and at this node is minus 10. Okay, so IE will be equal to minus 0.7, sorry, minus 0.7, okay, minus 10, that is the voltage across it by resistance is 10k. So it will be, so this will be equal to, so this is not 10, this is 20k. Okay, so given RE is 20. Okay, yeah, so the numerator will be now 9.3, and that is also, yeah, plus 9.3 by 20k. Okay, so what is 9.3 by 20? So it is like, it is equal to 0.465 milli. So that much is the current IE. So that is IC is equal to IE, right? So that is equal to 0.465 milli. So what is GM now? GM is IC by VT, or 0.465 milli by 26 milli. Okay, so that is equal to 0.1788. Okay, so GM is 0.01788 or 179. Okay, so that we will substitute here. So I have this small signal model. So how to solve this? So this, we have this current GM V pi, and is flowing like this, right? So it is flowing from bottom to up like this. So there will be voltage drop plus minus, and there is two resistance 10k. So what is the effective resistance here? 10k parallel 10k, so that is 5k. Okay, and so what is V out? V out is the voltage across this. So V out will be equal to minus GM V pi into 5k. Okay, and from the circuit, V pi is same as V in, right? V in is the voltage across R pi itself. So I can substitute it as minus GM V in into 5k. Okay, or V naught by V in is minus GM into 5k. So I'll substitute this GM that we have already calculated. So it is minus 0.01788 into 5k. Okay, so if I substitute this, I will get minus 0.0894 into 10 power 3, or it is 89.4. Okay, so 2. So this is the value V naught by V. So from the option that so there is minus here. So option is A. Okay, so thank you all.